Well, hello everyone, my name is Luke Wagner, I work at Fastly, and today I'm going to be talking about the component model, specifically this question of does the component model require extra copying? But first, since we're here at WasmCon, I thought maybe I'd like to start by just recalling why we're excited about WebAssembly in the first place. So in the browser where WebAssembly started, we can't run native code. Initially, we could only run JavaScript. So adding WebAssembly to the mix allowed us to compile our language of choice to WASM and get better performance than we could otherwise, which is especially useful if I'm porting a large existing code base. But outside the browser, of course, we can and do run native code all the time, so the reasons to be excited about WebAssembly have to be different. And at a high level, I think there are roughly 5. First, WASM can be a lot smaller than alternatives like containers, which can allow us to run that WASM on smaller devices. Or on large devices, pack more WASM workloads into the same amount of hardware to get cost savings, which is the second reason to be excited about WebAssembly. WebAssembly can also have much lower cold start times than alternatives like containers. For example, in Fastly, we could start a fresh WASM sandbox in under 35 microseconds, which is low enough that we can isolate every HB request by default. And this cold start can also lead to cost savings, because when you're not as scared about cold start, you can more aggressively scale to 0. Fourth, owing to its browser heritage, WASM is extremely portable, allowing us to run a single module of code across a wide variety of devices, including, by the way, the browser, where WASM effectively is the native instruction set. And this can also lead to cost savings because it allows operators to easily and dynamically shift workloads to run on lower power, lower cost CPUs. And lastly, WASM is great if you want to sandbox untrusted guest code running as a plugin in your system. By comparison, if you put the guest code in a container, you probably first have to wrap it in a micro VM and then filter outgoing network connections to make sure that the guest code can only access the public APIs you want it to have access to, and not the private APIs that are part of the inner workings of your platform. By comparison, if the guest code runs as WASM, it's sandboxed naturally just by the execution of the WASM runtime, which has a deny by default model that allows us to only explicitly grant access to the guest code to the APIs we want to make public, which is a great and simplified security model, and also leads to cost savings because the micro VM and filtering approach has real runtime overhead that makes the platform more expensive to operate. So that's 5 reasons, I think, to be excited about WebAssembly even outside the browser. But what about this component model? Well, first, just as a quick background definition, a component is a new binary format being standardized in the W3C that contains and links together a set of standard core WASM modules. So we can visualize these modules as being inside a component. And these modules can privately share linear memory and other low-level core WASM states, kind of like the native DLLs in a native OS process sharing the virtual address space of that process. And lastly, these WASM modules interact with the outside world solely through a new IDL called WITS, where the outside world can either be native code as part of the host, or in other components, which can have its own interfaces linked to other native code or components, and so on. And so that's what a component is. Why are we excited about them? Well, let's say I'm running WASM as a plugin in my platform, exposing to that WASM a set of APIs that describe my platform in a set of languages that my customers want to use. What I quickly discover is that work to build and maintain this grows quadratically as I add APIs and languages. Instead, with the component model, I can define those APIs once in WITS and then generate automatically high-level safe bindings in the languages my customers want to use. And this is like what people do today with OpenAPI and protobufs for remote procedure calls, but here we're doing it for local WASM function calls. So we call this use case SDKs for free. Next, in addition to being able to run customer components on top of my platform, I can also use components to implement features of my platform. And when I do this, I limit the blast radius of any bugs in that feature code, which then empowers me to ship and deploy these new features faster than otherwise. So we call this use case virtual platform layering. Third, if I'm an upstream toolchain developer who wants to generate WebAssembly, I probably want that WASM module to be able to both run inside the browser and outside the browser. But if I want to run in the browser, I'm going to need some JS glue code to basically do anything at all. And then, where does that come from? Do I have to put this in my upstream language toolchain? Or do I have to spin out a new project like mscripten is to C++? Or, this can be a large lift for the language ecosystem. And then second, how does this WASM module run in a pure WASM runtime that doesn't have a JS engine built in? Well, the component model provides answers to these questions. It says that an upstream toolchain can just produce a component binary that can either run directly on the WASM runtime, or it can be transpiled into JavaScript, glue code, and core WASM that runs in browsers today using a great tool called Jaco, published in NPM and maintained by the Bytecode Alliance. And importantly, this can run at the very end of a build step, just and automatically spit out the JS so that the upstream toolchain doesn't have to know or care about JavaScript. And so we say the component model gives us JS glue code for free. Fourth, because components have high-level language-agnostic interfaces with automatic bindings generation, they form a great basis for cross-language code reuse and building registries of these components for easy discovery. And then when I pull in one of these untrusted components, the sandbox nature of components mean I don't have to implicitly grant it access to the whole global scope and all the secrets hanging off of it, unlike most languages' native built-in package manager. And so we say the component model gives us secure polyglot packages. And then lastly, if I have a large application and I want some modularity in that application, one popular option today is to wrap the modules of code into different microservices talking over HTTP. But if all I wanted was strong isolation or cross-language interoperability, this can be a large amount of overhead. So instead, I could put those modules in separate components, talking over WIT interfaces, running in the same OS process, being able to make typed function calls in the same OS thread, which could be a much lower overhead and simpler operationally. And so we call this last use case modularity without microservices. So that's 5 reasons, I think, to be excited about the component model. But you may be wondering, at what cost? Because the key enabler here is that components are shared nothing, which means that they don't share low-level linear memory and other core WASM state between the components, leading to the question that we often get, which is, won't that require a bunch of extra copying? And this is a great question. And not coincidentally, it's one we spent a lot of time working on. So that's what I'd like to talk about today. So just as a quick outline, I'm going to start with how things work today in 0.2, move on to how things are going to work real soon now in 0.3, and then some why don't you just ideas that seem like good ideas but don't seem to work in practice, and then close with a few future ideas that hopefully will close the remaining gaps. So starting with 0.2, just as a little bit of background, 0.2 shipped in 2024. And onto 0.1, it added HTTP and socket interfaces. But also more foundationally, it rebased WASI onto WIT and the component model. And in this 0.2 release, the component model at a high level has 3 features. The ability to link together a set of core modules and components, value types like strings, records, variants, lists, and more, and the ability to find resource types, which are passed around by handle. And so I'm going to talk about all 3 of these in more detail and how they relate to copying, starting with linking. So we've been able to link WASM since the very beginning, because of course we can just compile multiple object files and feed them into WASM-LD, which produces a single core module. We call this static linking, and it doesn't require any special support from WASM or the runtime. So that just works, and we can take that module, feed it into WASM tools component new, and wrap it up into a component. But we can also take multiple WASM modules that were separately statically linked by WASM-LD, and then feed them into WASM tools component link to produce a single component containing multiple modules that can share a single memory. And that component encapsulates all the internal linkage state of those modules. And we call this dynamic linking. And so to see why I would even want to do this, we want to be able to factor out common code that would otherwise be duplicated via static linking into each component. So for example, libc, or the JS runtime, or the Python runtime, or whatever your language's runtime. These are great candidates for splitting out into separate common reused core modules. And these can be published via some sort of registry and shared by all these components. And in a cloud-native context, of course, the natural way to do this is with OCI, specifically the WASM artifact layout specification, and the Wagner tool maintained by the Bytecode Alliance. But in a browser context, this can be done with CDNs and the browser cache as orchestrated by your bundler tool of choice. But however it happens, at runtime, each of these core modules gets compiled to some machine codes, and then all the components that use the same exact core module can reuse the same machine code, just like traditional native dynamic linking, which is why we call it that. But regardless of whether we do it statically or dynamically, both of these kinds of linking are called shared everything linking because all the functions and all the modules share a single memory and can therefore pass raw pointers back and forth. And so this is something supported well by the component model. But also, as I said earlier, the component model supports shared nothing linking. And in this form of linking, I can take multiple components that are already built and link them together via a tool like the Bytecode Alliance's WAC to produce a new parent component that internally describes the linkage of those child components, keeping their memories disjoint. And because the parent component is just a component, it can be linked with other components with WAC again and again. And this is actually quite useful and necessary if you're doing virtual platform layering. But then taking a step back, if there's a piece of code that I want to reuse, the component model gives me a choice here. If it's in the same language, using the same tool chain, and I want to sling pointers back and forth, I can do shared everything linking. But if it's a different language, or I'm worried about API incompatibility, or supply chain attacks, or modularity, or virtual platform layering, then Maybe I want to do shared nothing linking. And if that's what I want to do, then I'll get to use the second feature of 0.2, which is value types. So to see an example of value types, let's say I'm defining a file interface with a read function that takes an offset and a length, and on success returns a list of bytes. All of these parameter and result types are all value types. So to see how they work, let's say I've got a component importing this read function. From a core WASM perspective, it'll show up as a core function taking 3 i32s. The first 2 i32s, not surprisingly, correspond to the u32s in wits, and wits just serving the role to clarify how to interpret the high bit in terms of sign. But the third i32 is more interesting. It's a pointer to a caller-supplied memory buffer that will receive this result value. But as soon as I start talking about memory, there's now a bunch of questions that I have to answer. Like, which memory? Because in WASM, there could be multiple. And is this a 32-bit or a 64-bit? Because that determines whether that's an i32 or an i64 pointer. Or maybe I don't want to use linear memory at all, and I want to use WASM's 3.0's new GC memory and GC types. So to answer these and other questions, the component model has lifting and lowering definitions that sit in between the high-level WIT types and the low-level core WASM types. And so, for example, my lowering definition here can say to use memory 0, which will be the index of some memory definition in the core module. And since memories by default are 32 bits, that's, we're using an i32 pointer. And now this i32 is unambiguously an offset into this particular memory that's allocated for this memory definition. And so at this offset that the caller chooses is where the result value will be written as 3 fields contiguously. The first is a Boolean that says on success, did this succeed or fail? And then on success, the next 2 fields represent that list value type. So where does that pointer point, and who gets to choose how that memory is allocated? To answer this, the lowering definition also specifies a realloc function, which is just a function in the core module that gets to do whatever it wants to do to find some memory in which to put the list elements. So for example, the realloc can just use the standard libc realloc, which is kind of the default, so that's why we named it realloc. Or it can use the language's linear memory GC allocator, which is what Go does today. Or it can use a caller-supplied buffer, which is what WASI-libc's read function does today. Or anything else. It's just a function that can choose where to allocate memory. And when it returns this offset, that's where the list elements will go. And so this pointer is written into the pointer field of the results. And now the component model will dutifully copy the elements of the list at this offset in memory. And so yes, as a baseline, there is a copy that happens with value types, and this is where it happens. But what we can observe is that in many cases, we already needed a copy, and the component model's not adding any additional copy over if I rolled my own custom core WASM interface. For example, if the bytes are coming from the kernel, then we had to copy into user space anyways, so we can just, smart runtime can make sure that copy goes straight into this offset in linear memory returned by realloc. Or if the host needed to maintain an original copy that was not modified by the untrusted WASM code, it'll need to make another copy. Or if we're using more complex value types where the layouts in memory aren't the same, then a copy might be necessary to transform layouts. In all these cases, we can just say that the component model makes the copy that was already necessary count. But now let's consider a case where that's totally not true and see how we can fix it. So let's say I'm defining an HTTP interface, and my request type is represented with a record, which is a value type that contains here headers and body as fields that are themselves value types. So this request is copied in full when I pass it around by value. And responses are defined similarly. And I've got an enum for error codes. Then I can define an HTTP handler interface that uses these types to define a handle function that takes a request and returns either a response or an error code. Now so I can now import and export the same HTTP handler face. The exported handle function receives incoming requests, and the imported handle function is used to make outgoing requests. But because I imported and exported the same handler interface, I can now chain up these components in the style of traditional middleware functions, which is like a great use case for components. But if request is a value type, then when the bytes come in over the wire, I'm going to have to fully copy into the first linear memory, and then fully copy into the next one, and then fully copy it out, and it'll go out of the wire, and come back and be copied all the way back. So that is potentially quite a lot of copying if all I wanted to do is poke at some headers, which is mostly what middleware functions want to do. So instead, I can use the third feature of 0.2, which is resource types. So instead, a better HTTP interface would represent requests as a resource type that's passed around by handle. In this case, I call methods on this resource to get fields and set fields. So I'm copying just the particular fields that I'm interested in. and I can define response similarly. And now when a request comes in, instead of copying it fully into memory, I just add a handle to a per component instance table and pass in the index of this handle to core WASM. Core WASM can then call getField and setField for just the fields at once. And when it's done, pass that handle to the next components, and the component model will transfer ownership to the next components, which can then call the methods, transfer it to the next one in the chain until it pops out to the host, who now has a handle to its own host-defined resource, so it can send it out over the wire to get a response. And then the whole process repeats in reverse as the response bubbles up the middleware chain. And so this is a much better than the previous example with all the copying, but it still leaves the question of what do I do about that request body? Do I represent it as just a list of bytes? Because if I do, I'm going to have to copy the whole thing all at once. And request, and especially response bodies, can be really large, so this can me. And maybe I only want to see the first couple bytes, and copying all of them would be a waste. Or maybe I want to see the bytes as they arrive in a streaming fashion. So to solve these and other problems like it, we now turn to 0.3, which we've been working on since last year and should be shipping any day now. And what 0.3 adds to WITS in the component model is async functions and the ability to have stream and future types in function signatures. And then using these primitives, we can rebase and simplify the existing WASI interfaces that we had in 0.2. And unfortunately, I don't have a lot of time to go into a lot more detail about 0.3, but if you want to find out more details, I gave a talk here at WASMCon last year called Incrementally Extending WASI 0.2 to 0.3 and Beyond, and at WASM.io earlier this year called Threading the Needle with Concurrency and Parallelism. But for now, I'd like to focus just on streams. So returning to my request resource, streams give me a clear answer for the body. I can say getBody returns a stream of bytes, and setBody takes a stream of bytes. And so to see how this would work, let's imagine a component that's holding and owning a handle to a request. And now I want to call getBody, which in core WASM has this signature. It takes an I32 and returns an I32. The first I32 parameter is the index of the request whose body I want to get. And then when I call this, a new stream handle will be added to my table, and that will be the returned index. And so now that we can see that streams are like resources in that they're passed around like by handles. But unlike resources, which have an open-ended set of user-defined functions, streams have a fixed set of built-in functions, like stream.read, which I can pass it with the signature. So the first I32 is just the index of the stream that I'd like to read, and the next two I32s are a delimity buffer in memory that I'd like to read the stream bytes into. And then the return value says what happens. So either in the happy, fast, eager case, there were bytes ready to go, so they were copied right away, synchronously, and the return value just says how many bytes were copied. But if there weren't any ready, the I32 return value will be a sentinel blocked value that says the stream is running in the background concurrently. You can keep running in the foreground. And so let's say this component is running in a user space process, and the stream is connected to a device owned by the kernel. And let's say for fun, the host WASM runtime is using IOUring to implement I/O, which shares a submission and completion queue between user space and the kernel. Then stream.write or stream.read can simply append a read operation to the submission queue, and the address will point directly into linear memory. And since stream.read is a non-blocking operation, if I have multiple streams, I can kick off multiple concurrent reads. And now when bytes arrive physically on the device, the kernel is fully empowered to copy them all the way into user space directly into the linear memory location that I passed concurrently, which is pretty good. And you would say, like, this is about as good as you could hope for. And so the component model in this case is not adding any extra copying beyond what was already kind of fundamentally necessary. So that's what we've done in 0.2 and 0.3 to avoid unnecessary copies. Now I'd like to consider two options that we haven't done, even though they initially seem like potentially good ideas. And the first is to lean heavily into multi-memory, now in WASM 3.0. And in this idea, if I've got two modules, they have their default private linear memory, but they also share a non-default shared linear memory that they can use to pass complex values back and forth without copying. But the challenge here is telling the compiler at every load and store which memory to load and store from. Because not by itself, an I32 is just an offset. It doesn't say which memory it's an offset into. So one option to tell the compiler is to put the information in the static type. For example, in Clang, I could use the address space attribute to define a shared macro, and then put the shared macro on all the pointers that point into the shared memory. But the challenge with this is now this shared macro has to follow all the pointers transitively wherever they go throughout the whole code base and be exactly right, because if I get it wrong, I'm going to get like memory corruption. And this might be a lot of code and take me into library code that I can't control or change. So this approach requires some pretty invasive code changes and doesn't work, or might not work as well as you would hope. The other option is to put it dynamically into the pointer and change the representation of the pointer to encode this information with the fat pointer approach. But this approach has some performance overhead, because now we have a little more dynamism on every load and store, and it requires more intensive tool chain support, so it's also hard to make work in practice. And if I don't do either of these approaches, well, then I end up doing 2 copies from my default memory into the shared memory, and then from my shared memory into the default memory. And so in the worst case, this, or perhaps even common case, this would be worse than the 1 copy we would get from the component model. So while attractive in theory, this seems hard to make a win in practice. And the second option is use the operating system's mmap, or map view of file, where we could just, you have just one memory, but we map a shared region into that memory or map files into that region. But the challenge here is portability, because fundamentally, to be at all efficient, mmap needs some sort of MMU hardware in the CPU, and a lot of the hardware that people are running WASM on today simply does not have an MMU. And furthermore, that MMU has to be exposed to wherever the WASM runtime is running via the OS, and not all OSs expose it fully. And since portability is a key value proposition to WASM, this seems like a major problem. There's also performance hazards with mmap. It's a syscall that takes kernel locks, and it changes virtual address space, so it needs to perform TLB shootdowns. And if I mmap a file, this can mean doing synchronous file I/O on page faults. And for more on this, see this great paper titled, "Are You Sure You Want to Use mmap in Your Database Management System?" But suffice to say, performance is a hazard, particularly on highly concurrent systems. Fortunately, though, mmap is not the end of the story when it comes to mapping memory. And there's a more minimalist memory mapping approach I think that's worth considering. And to be clear, this is the final speculative, probably wrong, post 1.0 slide of the talk. But the idea starts with a really cool feature of Wagner called shared heaps. And to explain how it works, let's start with a normal linear memory, which a WASM engine will usually represent by a pointer length pair at some host memory that's used to implement the abstract WASM linear memory, such that if I load from an I32 offset, it's added to that pointer to compute the actual host address to load or store from. And if I load outside the length, then it traps. Well, what shared heaps adds is a second shared pointer and shared length that can point to a totally different region of memory that can be shared between different modules. And then this can be mapped into the same linear memory at a higher offset, leaving a trapping hole in the middle that can shrink over time as the unshared region grows. And now if I load at a large offset into the shared region, I can take the offset into that shared region and add it to the shared base pointer. And so this does add a little bit of extra dynamism and indirection, so some performance overhead. But in exchange, it doesn't depend on any MMU or OS supports beyond what normal core WASM does. It allows super fast mapping changes. Instead of making syscalls that take locks and flush buffers, I can just update 2 pointers. And it can point to any memory, not just files with backing file descriptors. For example, in the browser, this would allow me to map an array buffer, which is like a use case we've had since the ASM.js days. So this seems like a pretty cool idea and a good trade-off to make. But unfortunately, it's not allowed by the WASM standard at all at the moment. But there is a memory control proposal exploring different ways to generalize the existing linear memory. And one of the sub-proposals already has this concept of saying, what if our memory definitions could have a mappable attribute? And when you set mappable on a memory, that would allow you to use memory map and unmap instructions, passing it a reference to a buffer you'd like to map. Well, a small tweak to this, proposed in issue 21, is to say you could only map at most 1 buffer at a time. If you want to map a second buffer, you have to unmap the first, which again is a very cheap operation, so you can ping pong back and forth just by mapping and unmapping. If we make this restriction, then we can use the above implementation technique. So this seems like a potentially pretty cool and promising approach, I think. But there's, of course, a lot of details to work out. But let's say we do get something of this form into WASM. The next question is, how do we lift it up into the component model in WITS? And the idea, discussed in component model issue 568, is in WITS we could add a new type that I'll tentatively call the byte array type. And a byte array would represent exclusive ownership of a mappable region of memory. So this transform function would be given ownership of the byte array so it can map it, do whatever it wants, unmap it, and then return it. Or it can make a streaming pipeline by defining a map function that takes and returns a stream of byte arrays. And then to see how this might work, imagine I've got a streaming pipeline of components, and I've got some memory, host memory that I'd like to send through the pipeline. I could create a handle to a byte array to this, send it through the first stream to the first component, which can map it, load and store, unmap it, transfer it to the next component, which could map it, load and store, unmap it, transfer it out. And now the host has exclusive access of its memory again. And what's really cool about this is it allows zero copy passing of large amounts of bytes between components with the exclusivity preserving the shared nothing property that I talked about at the beginning, which is the important thing for all the great properties of the component model that I mentioned at the beginning. So unfortunately, that's all the time I have to talk about this particular idea. But hopefully it shows that there are feasible options to close the remaining gaps. And so, in conclusion, the component model provides values and streams that allow us to make the copy that was already necessary count, as well as shared everything linking, resources, and hopefully one day byte arrays that allow us to avoid copying altogether. And so returning to that original question of does the component model require extra copying, I would say no, mostly, to quote the movie Aliens. But it's worth it, and it's going to get better over time. And so that's it for me. Thanks for your time, and if you want to dig in, here's some cool links. Thanks.
Thanks a ton, Luke. I'm Ralph. I'm going to do some of the moderating in between sessions today. We have like about 5 minutes while the next speaker comes up. So if there are questions from Luke, for Luke, if you don't have any questions, great. Good.
Oh, that's the WebAssembly micro runtime.
Go ahead and repeat it. So WAMR is?
Bailey asked, what is WAMR? And WAMR stands for the WebAssembly Micro Runtime. It's a bytecode aligned project for running WASM in very small devices.
Other questions? Great. Thanks, Luke.
Thank you.
Appreciate it.